Hello, everyone. This is Chad Walber with PCB Piezotronics, and then welcome to this afternoon's Advanced Acoustics webinar. Let me go through some of the topics we're going to go through today. Advanced Acoustics basically takes some of the stuff we've seen in basic acoustics, and I talk about it kind of on the next level. So there's going to be a little bit more math. There's going to be kind of some funky new drawings and stuff that I have in here, and let's get started here. Also, I will state, if you have any questions, please leave them in the chat box. You can either chat directly to Jennifer Carlo, or you can go chat to everybody, and we'll try and get to your questions at the end. All right. So to start out, in acoustics, as always, we kind of have this model of source path receiver. We talked about this very generally in basic acoustics, where your source is a system that is creating sound. The path is either the air or the structure around the source that is carrying the sound to the receiver, which is either an ear, another structure, or a sensor. And in this case, we're going to start from the receiver end and work our way back. And we're going to talk about measurements and what you're going to do with those measurements in order to make sense of them in your own post-processing. So I'm not going to talk about microphones here. That's another webinar. But I am going to talk about what you're going to do with data that you get from your microphones. So when you do a sound pressure measurement, you're using measurement microphones, and you're converting a local sound pressure to a voltage. And when I say a local sound pressure, you don't have sound pressure information of the entire room or the entire environment that you're working with. You're measuring a single point in space. And that single point in space, the response that you're getting will be dependent on what kind of microphone you have, what kind of reflections you have in the room, and that will all will bleed into your measurements. But that's just the voltage. You also now have to take that voltage and measure it somehow. So in order to do that, you need to have a data acquisition system. I mean, you could use a voltmeter and just write numbers down over time, but a data acquisition system will sample your data at consistent intervals and give you accurate voltage depending on the bit rate that you're measuring with. And then now you have a log of all this data of voltages coming from your microphone. You can calibrate your data so that you know the proportionality of your microphone to the voltage output of your microphone, which is your sensitivity, and then you can perform data analysis. And octave band analysis I talked about in a basic acoustics. Sound pressure levels, basic sound pressure levels is just doing an RMS average of your data, and that's easy enough to do. You can do time-weighted and you can do frequency-weighted data. And then what I'm going to do next is I'm going to dig into a little bit of the Fourier Transform. And the Fourier Transform, what we're going to look at mostly in the Fourier Transform is the frequency data. And many of you should know frequency is the number of repetitions of a point of a sinusoid over time. To scale the frequency properly, for the sinusoid formulation, 2 pi is multiplied by the frequency to convert to radians, because sines and cosines can't take just hertz. You have to put the 2 pi inside of there because it has to be a unitless number, which is radians. And then also you have the period, which is 1 over the frequency. The phase, and there's going to be a couple different definitions of phase that we're going to use. The first is the fraction of the sinusoid that has occurred relative to the start of the cycle, and then also the initial angle of the sine or cosine function. So the other definition of phase that I'm not going to cover as much here will be the difference in phase between 2 sinusoids. Phase is always measured in degrees, and so it's going to be scaled based on what the frequency of the signal that you're looking at is. So 5 degrees at 50 hertz and 5 degrees at 500 hertz actually have different time bases. So that's an important thing to try and tease out of there. And phase A lot of people work in degrees, but again, sine and cosine functions want radians. So you're always going to be working in radians with what's going into the sine and cosine functions. So now to get to the actual Fourier transform. And the definition that I have here is one of the most simplest definitions you can come up with. It's a form of signal analysis that converts a time-based signal into amplitudes and phases at the signal's constituent frequencies. And there's the Fourier transform, and then there's also the Fourier series, and I'll talk about that a little bit as well. Like Taylor series, signals and waveforms are a summation of many different things. In Taylor series, you're talking about polynomials. In the Fourier series and Fourier transforms, you're talking about summations of sinusoids. And then individual frequencies are indications of various acoustic phenomena. And that's why we look at the frequency domain, because we study sinusoids so that we can get various information about frequency. So again, like similar to Taylor series, the Fourier breaks down the signal into its constituent sinusoids. And this is actually an equation at the top here of the Fourier series. And so you have the first component, which is your DC component, meaning 0 hertz. And then everything above that is you have a magnitude, which is a sub n, sine or cosine of 2 pi n, which is each integer in the series, x, and actually that's an error, that should be a t, not an x, and then p, which is a scaling constant that tells you what your frequency step is. And then you also have a phase associated with that. So in your when you plot your Fourier transform, as you see in the plot below, you will get different pokes, different little stems popping up from the line that shows the amplitude of the particular frequency that we're looking at. And each of these, when you take that sinusoid and you plot that sinusoid over each other and then add them up, that gives you this wave response here. And you can see that we can actually split it out. There's all the waves are built right into there. And that's the summation of all the sines and cosines. And in fact, mostly with what you're dealing with is either sine or cosine. This one has sine in it, but you can do cosine, and then your phase is just going to be 90 degrees different. And you see, you just add them up, and that gives you your Fourier transform. Fourier series is the group of sinusoids that you add up to create your signal. The Fourier transform is a plot of the magnitude of those sinusoids. So it's a very subtle difference there. In most cases, we will not ever be working with a Fourier series, but know that the Fourier transform is ultimately what that breaks that down to. So how does this apply to acoustic waves? Well, acoustic waves at the end of the day are sinusoidal. Most of the time what we're dealing with, we're looking at sinusoids. Whether it's music, whether it's various phenomenon for machinery. Rotating machinery is generally sinusoidal in nature. And so what we have in this graphic here, thanks to Dr. Dan Russell from Penn State, is basically just kind of a nice graphic, and I can see on the screen it's kind of bouncy back and forth, not as clean as it could be, but you're getting the point. Is you have a waveform that starts at the left and works its way slowly across to the right, but you'll notice that there's no flow. Imagine that these are particles of air. The air isn't actually moving with a net flow, it's just bouncing back and forth. And the way that bouncing back and forth is working, it happens to work out that you've got high pressure areas and you've got low pressure areas. And if I had a microphone at a specific spot over here, like where my cursor is, I don't know if you guys can see that, but what it does is, if I had a microphone there, as the wave goes by, I'm measuring what the sound is doing at that particular point. So when I said earlier that we have a local measurement, that's exactly what I'm doing. I have my microphone in a very specific location, and now the sound pressure is changing about that location. But even further, again, you see the individual red particles that are just kind of bouncing back and forth. Those represent a wholly other phenomenon. So while the density of the air, which, again, this is a change in air density, is moving across. So you could plot that as well. But what we can measure more easily is sound pressure. But the motion of the particles back and forth has a velocity to it. And that later we can tease out, and that will give us particle velocity. Just the motion back and forth of these particles back and forth is the particle velocity of an acoustic wave. So what is a wave? And very simply, it's a disturbance that travels from one location to another. And there are lots and lots of shapes of waves. Again, I go back to Fourier series, Fourier Transform. We're going to talk about sinusoids here because they're one of the easiest things for us to study here. And you'll notice in this diagram here also that pretend this white line is just a measurement point with my microphone. And as the wave travels past it, the amplitude goes up and down and up and down. And that finishes up the wave that we have, the signal that we have in the bottom left plot. Then what we can do is we can say, let's look at the entire room and take a screenshot of what the room is doing across multiple points. So imagine I had some sort of magic camera where I can measure the sound pressure at various places in a room in one shot. That's what we have in the lower right here. Over position, you have increases and decreases in sound pressure over the space. And of course, it wouldn't look like a sinusoid like this. You would see more something akin to what you see up here, where you have density of particles moving back and forth. So you would have really dense spots, and then you would have really loose spots where you got the particles moving back and forth. So this is where the math comes in. There's an equation for waves, and it's specifically called the wave equation. It's a second-order differential equation in time and space. The symbol on the left here stands for a partial derivative with respect to x, y, and z, and x, y, or rather to your three spatial coordinates. So you could make that into Cartesian, which would be x, y, and z. You could make it into cylindrical coordinates, and you could make it into spherical coordinates. And later on, there are various reasons why you would do that. And mostly it has to do with what kind of source you're looking at, or what kind of sound field you're actually interested in looking at, or the shape of the room that you're in. So it all matters. But in this big complex equation here, with differential equations, we care less about how to get the equation into a form that's interesting and easy to move around, but what we care about more is what's the solution. And in the case of the wave equation, the solution is actually pretty simple. It's the pressure, which is what we care about here, is and you'll note I only have one variable for space here and a variable for time here. But in the end, the function of P of RT is any function where you have omega t, where omega is your rotary frequency in radians per second, minus plus, and I'll get into why it's specifically that in a second, K, which is wave number, times R. And note that everything in this function has to be dimensionless. So that means the units on K are 1 over whatever the length units are on R. And the dimensions on T, which are seconds, has to be cancel out the omega, which is radians per second. So that gives us all of our dimensionless numbers in here. Now, what we generally do to even make our lives simpler is we assume a linear time varying solution. And we give it this form down here. A lot of people will recognize this as Euler's form. And the minus is it's a wave that's moving away, and the plus is a wave that's moving towards us. And most of the time we're dealing waves that are moving away from a point. You would use incoming waves sometimes for microphones, but usually you don't want to model your microphone inside your, unless you absolutely have to, inside your analytical model. So you just put a point in and you assume that that's the point where you're taking a measurement. And we further simplify this down to, okay, I don't care about the incoming wave, so I care about the outgoing wave. So when I look at the Euler form here, I take that even further to A e to the j omega t minus kr, and that's equal to A cosine omega t minus kr plus JA sine of omega t minus kr. And this is the very, very simplified form. I don't have any phase differences in here yet. This is assuming that the wave is starting at 0, and then or I have it's going to be affected. The phase is going to be affected by where it is in position. So that's the equation that you're going to use to mathematically describe a wave. And R can be a vector, so this could actually not be just one set of equations of cosine and sine, but it can also be spherical sections of cosine and sine. It can be Cartesian. There's a lot of ways you can go with this. But I am not going to cover that in this webinar because it would take too long. So what I'm going to talk about a little bit more is wavelength and what it actually means in these equations. When I talked about earlier that frequency we're looking at over time. Well, you can also do the Fourier transform of a wave or a sinusoid over space. And that what you're looking at there now is wavelength and wave number rather than frequency and period. When the frequency, again, happens spatially, repeating over a certain distance, that's the wavelength. And the wave number is the wavelength times 2 pi. And again, 2 pi is to get back into the radians equivalent. The wavelength of the wave is the speed of sound divided by the time frequency of the wave. C in air is 343 meters per second at standard temperature and pressure. Notice I have those two things in there. Furthermore, I can say at specific concentrations of carbon dioxide and humidity level because all of those have an effect on the speed of sound in air. Elevation has an effect on the speed of sound in air due to the ambient pressure that you're working with. So all of these things don't necessarily affect the peaks of the waveform, but they do affect where your zero lies. And that's ultimately what you're interested in with some of your things in the wave equation, because that will have an effect on your speed of sound. Talked about particle velocity earlier, and it's exactly as I have it described here. If you take a chunk of air and you watch as it's moving back and forth in the fluid as a wave goes by, that physical speed of that chunk of air is your particle velocity. Now there's two parts of the particle velocity. One is the magnitude of the particle velocity, which is how fast it is at its peak, and that will also be described as a sinusoid. The second part of particle velocity is the vector direction. So let's imagine I have a magic probe that measures particle velocity, and in fact they're not really magic, they actually make them. If you take that probe and rotate it 180 or 360 degrees, when you know there's a sound source perpendicular to it, what will happen is as you have it turned 90 degrees to the sound source, the probe should read almost 0 because it's measuring particle velocity in a specific direction. As you turn it 180 degrees from your origin where you had your maximum, you're actually going to register a negative particle velocity because the vector is moving in the opposite direction of the probe. And you can ultimately determine your magnitude of your particle velocity knowing that if you're working with a plane wave, and only if you're working with a plane wave, and we'll talk about what a plane wave is in a little bit. So if you have a plane wave and you know your ambient, or you know your sound pressure and the density and the speed of sound, you can calculate what your particle velocity is. There are other methods in performing the sound intensity measurement using those types of measurements. Particle velocity ultimately falls out of the procedure when you do sound intensity. So just to recap what we're looking at with the wave here, your wavelength, and again, this is not over time. This is happening over space. And so c is your direction of motion of your wave, and your wave is moving at the speed of sound. This particle right here is moving back and forth, and I have it shown kind of as a displacement, but u is actually a velocity. So the peak velocity of u occurs right in the middle of this motion, and that would be your particle velocity. And then I have here what approximately would be your wavelength. And as you see the two peaks go by, you see that that matches up very, very well. And you can see the compressions and refractions in this going back and forth. And you can see that each wavefront, the other term that you can call this is a phase front, is traveling across the screen. And this is how we go from our receiver to our path. So let's talk a little bit more about what's going on with our path. Plane waves, and we talk about plane waves because they're probably the most simplistic versions we can model. And in order to actually have true plane waves, you will have low frequencies and pipes and ducts. If you're very, very close to a really, really big source, like a panel vibrating back and forth, that will be a plane wave. Also, if your source dimensions are also bigger than your measurement distance, you also assume that you're working with plane waves if you're at a very great distance away from a spherical source or a point source. Because what ends up happening is the phase front, as it gets further and further away, it becomes less curved and almost flat. And those types of waves, that's generally what we work with when we're talking about sound power measurements. We like to assume that we're at such a distance away that we have a plane wave coming at each microphone. Or when you're doing a free field calibration of a microphone, the assumption is that the microphone is measuring a plane progressive wave. If you ask your questions, I just saw someone raise their hand. If you ask your questions in chat, I will answer them at the end. Cylindrical waves. So I go back to, so if in the wave equation, a plane wave would be something you would model very nicely with in Cartesian coordinates. Cylindrical waves are modeled mostly around vibrating cylinders, pipe noise, strings. Again, the source length will be much larger than the measurement distance. Other things that are modeled as cylindrical waves are roadways. So if you have a very long bridge and you have cars traveling on a roadway, that can be modeled as a cylindrical wave, because as the noise comes off of the bridge, that will radiate out in a cylindrical fashion. So traffic or train noise, also vibrating strings. And again, you could model this as in your wave equation with cylindrical coordinates rather than using Cartesian. And then lastly, you have spherical waves, which again, you could use spherical coordinates in your wave equation. Close to vibrating spheres or spheres, sorry. But we normally look at it, it's like, okay, we like to treat our sources like they're point sources, mostly because they're easy to model. And this happens when we generally get in the far field from any type of a source. And again, the source dimensions are usually much smaller than the measurement distance when we're talking about spherical waves coming off of point sources or spherical sources. And in fact, there's a lot of different builds for various spherical sources out there, and they're very good for test builds for doing testing in noise chambers. The speed of sound. This is acoustics, so the majority of what we're going to work with is going to be in air. However, basically every material has a speed of sound as one of its material properties. Strings are the tension, the square root of the tension divided by the density of the linear density. Gases are the ratio of specific heats and the total pressure divided by the density, square root of all of that. Liquids, again, it's the ratio of specific heats times the bulk isothermal bulk modulus divided, again, density. Density is a big part of what goes into the speed of sound. And density ultimately is what is affected most between the ratio of specific heats, which will have a big impact. The densities of the material will actually have the bigger impact on the speed of sound of that particular material. And then in solids, strings are solids. So when we've all done when we were kids, take a tin can and tie a string to it, pull it tight, and speak into it, and listen to your buddy on the other end. You're basically sending a sound wave up and down a string. Characteristic impedance. I put this here not because we're going to sink into it very deep, but more because it's important when it comes to a bunch of different measurements. Particularly sound intensity. If you're going into sound propagation, characteristic impedance is important because ultimately what you're going to do to solve your models is, it's going to you're going to set up basically a circuit where you have your input is your sound source, and then you're going to propagate your wave across a series of acoustic impedances. So if I have a source in one room, I'm going to propagate the sound across the acoustic impedance of a specific room to the wall, which has another acoustic impedance, and then I'm going to propagate it through the next room until I hit the point where I'm going to do my measurement. Specific acoustic impedance is a ratio of the acoustic pressure to the particle speed. And again, for plane waves, and the reason we have that is because it's basically the most common, it's the easiest thing to model for most of our stuff. So, and again, sine is based on the propagation. You're either going to have your average density times the speed of sound.
2623, go ahead, 2623.
And then in less idealized cases, you're going to have to tinker with what your geometry is doing and how that's actually affecting your the characteristic impedance of either your room or of your entire model and your structure.
Dave Dershberger, please call 2419. Dave Dershberger, 24.
Sound intensity is the instantaneous intensity of a sound wave, and it's basically how much flow of energy do I have acoustically through an area. And you can treat it like it's a Gaussian surface, and then either measure, or even over the course of doing a model, you can propagate your wave through it, and you can determine what your sound intensity is through that. The units on sound intensity are watts per meter squared. If you measure I call it a Gaussian surface because I started as an electrical engineer, which is a surface that you put around your sound source, and you know what your wattage of your sound source is, and you know the area of your sphere. If you measure the chunk of area at the sphere you're looking at, your intensity at that spherical surface will be I is equal to the sound power of the source of the and then divided by the surface area of that particular sphere. When you make the sphere bigger, the sound intensity will go down, which makes sense. If it's a spherical source, the further away, the less intense the sound source. You can also do the time averaged intensity. It's very akin to doing the sound pressure level, but now you're doing a time averaged intensity level, and ultimately you would take that into decibels. And you see here it's you have to take into account the direction. So if it's going away from the source, it's positive, and if it's going to the source or the direction that you care about, it's negative. P squared RMS over rho C, again, you're assuming at this point that it's a plane wave. note that it's also equal to P0. In this instance, P0 isn't your specific sound intensity or your specific sound power of 20 micropascals. P0 in this case is the peak sound pressure of the sinusoid. So again, the sinusoid that you're looking at the particular frequency that you're looking at, you would use the peak instead of the RMS level. And that's the reason you have the factor of 2 in the bottom, because your peak is actually going to be 2 times, is going to be the square root of 2 times divided by your RMS level. And you see that this is the whole integral thing, and it's all built in. All of the math into the sound pressure and the particle velocity for the time averaged intensity is built in here. Because if you remember, U is just equal to the sound pressure divided by the density and the speed of sound. So again, you go to intensity level, and IL, intensity level, is in dB, 10 log of I over I0, where I is your sound intensity, you got your time average sound intensity, and I0 is 10 to the negative 12 watts per meter squared. When you're doing a sound intensity level measurement, there's a number of ways to do it. The top method is you're basically measuring at a bunch of points and you're doing a summation. And the interesting thing you can do with that after you're done is you can take those measurements and you can use them to create an image of the sound intensity coming off of your structure. The important thing to note whenever you're doing any type of sound intensity measurement is that your background noise needs to be constant. That's not to say that you should turn on a noise source and have it always be on. But what I'm saying is if someone's doing work in a room next to where you're doing the sound intensity measurement and you finish half of your measurements, go to lunch, and you come back and that person's still not there doing the same type of noisy work, your noise measurements will be completely off. You will actually have tainted them because half of your sound intensity is measured one way and half of your sound intensity is measured another way. Another way of doing sound intensity measurements is basically just tracing back and forth over each surface of your Gaussian surface, and then using that in order to average your sound pressure and sound intensity data over the entire face. Sound intensity, it's a very good and a very accurate measurement. There's a couple caveats. It's a pretty tedious measurement, requiring that the probe is moved fairly repeatably. Positioning of the probe can be kind of a pain. Again, if you want to really set it up well, gantry systems will help automate the process. And then also local positioning systems are very helpful in doing sound intensity measurements. So I'll talk about directivity here. So once you have your source and let's say you've worked on a noise source or you're looking at a noise source, what you want to know about it is where is the sound coming from on the source. And intensity can give you localization, but also what it can give you is the directivity of a particular source. So let's say you know exactly what your sound source is, and what you want to do is say, all right, if I rotate the sound source in a particular direction, does it make more or less noise? And so what you can do is you can adjust, you can take measurements in various degrees around your sound source to determine what the directivity factor is. If it's, let's say you have a line source, it's got a fairly big directivity factor in one direction, but the rest of the directions are pretty much the same. Or a sphere. A spherical source actually has 0 directivity factor, because no matter which side of the sphere you're measuring on, everywhere you stand, the sound pressure level is the same. When you talk about the directivity of a circular piston, so a baffled piston, it's all going to matter Ka, which is A is your, I believe it's your diameter of your piston. Yep. And if your distance is very close to the piston, so Ka is your characteristic distance from the piston, your directivity is 2 and your directivity index is 3 dB, meaning if you're if you're real close to the piston, if you're in front of it or off to the side of it, you may have 3 dB of difference of what your sound measurement is. If you're a far distance away where Ka approaches infinity, then your directivity is equivalent to the square of Ka. And so, and that's just one example. Various sources, and they do this with speaker cabinets all the time, making sure that your directivity, all of your sound needs to be pointed toward you, and making sure that you're not necessarily like wasting any energy with your directivity going in a different way. And then the opposite is done with various noise generating machines. You want to make sure that your noise is away from whoever's using them because you don't necessarily want to expose them to that kind of noise. And then the last topic I'll talk about today is arrays. Array setups are a series of microphones that you have spaced out either at in a specific configuration, and the noise that comes from whatever your source is or whatever you're measuring has a slight delay due to the distance between the microphones. Time signal is simultaneously recorded at all of the microphones, and then due to that phase delay, you can use that to backtrack and learn where in space your sound source is. There are limitations on this. Low frequency measurements are limited based on the wavelength that you can measure with your array. So the bigger array, the lower the frequency you can go. At the same time, you have the same problem with high frequency measurements that you have with sample frequency. So if you really want to measure really high frequencies, it's completely dependent on what the sample frequency is. So whatever your frequency of interest is in time, you double the double that, and that gives you your sample frequency. And in fact, you want to go more than double because you want to get more fidelity in that waveform. High frequency is the same way. So the interspatial distance between each microphone and array will have an effect on what your high frequency measurements are. And in fact, you will get a spatial aliasing problem if you don't have your microphone spacing correct. And that's all I have for today's webinar. Thank you all for coming in and listening to me. If you have any questions, I'll hang out here for a couple minutes. Please submit your questions via chat. That's usually the easiest way. Unmuting your microphone, otherwise we have multiple people talking at the same time. It doesn't work out very well. So I'm going to mute my channel right now, and if we see anything in chat, I'll respond to it, and otherwise have a wonderful afternoon.